All right. Thank you everyone for your time. I'm Priyesh Gosai, as Lucas mentioned. Um, I founded a company called Innovate for Impact, and I'm also a director at a company called PAS Automation. So my background is that I was a power plant engineer at Eskom, the South African power utility, in the start of my career, and then worked at the University of Cape Town as a research officer in thermal fluid process modeling. And then in 2022, formed Innovate for Impact, where I've been developing numerical models for energy for energy systems and thermal processes. I spent a bit of time at Open Energy Transition and recently joined PAS Automation, where we are developing low-cost cloud-based solutions for asset monitoring. My clients include the International Center for Hydropower, the Japanese utility TEPSCO, Energy Nautics, Chown and Associates, and Energy Lab based in Asia. So let's talk about what is hydropower. So at the moment, we've got around 1,469 gigawatts of installed capacity of hydropower globally, of which 201 gigawatts is pump storage, uh, almost 4,500 terawatt hours of annual generation, uh, 1.1 gigawatts capacity and under construction. It accounts for 14% of global electricity generation, and 28 gigawatts alone were added in 2025, of which 12 gigawatts were pump storage. And typically, these facilities have lives of as long as 100 years. So they're extremely long-term solutions for our energy crisis. So we can break down hydro plants into a few characteristics. You firstly can look at runoff river. So you have a river where you install a diversion, and you can take a portion of the water through the diversion and pass it through a turbine. The turbine turns a generator and produces electricity, and the discharge is then released downstream in the river. If you want to add some storage, you've got to have an impoundment type uh, hydro plant where you've got to build a wall and then control the flow in and out and store a large amount of the water behind the wall such that you can then have either daily or even sometimes seasonal storage, which is very, very useful in certain regions. And then there's the idea of pump storage. So instead of just having one dam, you have two dams, an upper and a lower dam, and you would pass water from the upper to the lower dam to produce electricity, store that water, and when electricity prices are low or when there's an excess in electricity, you can pump that water back up for the next cycle. And these also have an open and a closed loop, where the open loop allows water from the external environment to keep flowing in, and the closed loop would just be two dams that operate kind of outside the environment, not always completely, but in some way or form. So water uses, power has water uses beyond just electricity, or hydropower has water uses beyond electricity. It's used for water supply, flood management, irrigation, and recreation, and all of these things need to be often taken into account. You get a huge variety of them of configurations. So you can have different configurations of the types of plants. And so geographically, or if you look at it from GIS perspective, you'll not be able to recognize each plant is exactly the same. And when you put lots of them together, it becomes a cascade. So what do we have? We have to firstly convert the water flow rate into power. And essentially, the fundamental equation is the rho GH times the flow times efficiency. And what I typically define is what we call rate 2 in the process component, which is the power over the flow rate. The efficiency typically is a function of the flow rate, so that can become a bit complicated. But we'll always need to simplify things for our energy system models. And as a result, if you simply take a hydro generator, which has a rated flow and a rated discharge, rated power, you can very basically calculate the power over the flow. And this assumes that the efficiency, the operating efficiency is constant, which is kind of true for a broad range of the operating range of a plant. And it excludes the effects of head. So the level of the dam also affects the total power output. Typically, what I'll do in this is I'll correct it through successive approximation techniques after the solution has been produced. So There are a few ways you can model hydro plants in PyPSA. The one way is the storage unit component. It's quick, it's easy, simple. Um, you take the inflow variable in the component, and you can set that inflow variable in million meters cubed per hour, and then use the efficiency discharge variable as the conversion factor. So that would mean that the efficiency is sometimes greater than one, but it you have to reframe your thinking as though that's a conversion rate and not an efficiency. In that way, you measure your inflows in millimeters cubed per hour and your discharge or your energy produced in megawatts. Um, and for non-pump storage plants, you'd have to set the efficiency store. That's the efficiency at which the plant, the storage unit extracts electricity from the grid to zero, and that stops any inflow of electrons to the hydro plant. And you can also monitor the spill. If you want to do something a bit more complicated, you can explicitly represent it. So a single plant will be represented by a bus, an inflow generator, an outflow generator, or river inflows, as well as process components to represent the turbine as well as the spill. For cascaded plants, you would do the same thing, and you can interlink them with the river component that has the fantastic delay feature that was recently added in PyPSA version 1.2. So all of the process component features are only available from PyPSA version 1.2, so just make sure you update it. Um, and you need to set the rate zeros, rate 1, and rate 2 accordingly. So for me, it's worked to set rate 0 to -1, rate 1 to 1, and rate 2 to the P over Q ratio that I discussed earlier. So a case of a single dam. So I've been running simulations on multiple dams across plants in Asia. So this is a case on a single dam, and we've had to take into account a lot of additional constraints. So you'll see that the bottom chart here has the dam level over time. The top right chart has the dispatch, and we need to keep the dam level within a certain range that is set by the regulator to ensure that the dam is able to release water during floods. So these operational constraints need to be taken into consideration, put in based on your Emin and Emax constraints, run the model, and you can keep all of these simulations, keep all of these constraints into the simulation. You can then expand that into a cascaded system. So in this case, I've got four plants. You've got each an inflow at two plants on the top of the cascade that connect into a third plant, and eventually discharge out of the system. You can even have inflows intermediate to that if you have measurements. So for pump storage, this is an interesting case. So coming from South Africa, we've got large amounts of coal. And in the days of coal, when coal first started, you would not want to ramp the coal plants up and down. And we switched on and switched off a lot of to avoid switching on and switching off your coal plants, we installed pump storage. And this has meant that pump storage was traditionally used in this capacity. In the nighttime, when there was excess electricity, we would run our pump storage. And in the daytime, and that pump storage would then be providing the peaking capacity. However, if you start increasing the amount of solar into the grid, that profile shifts where you start pumping, you start pumping during the day, and you use that electricity for the evening and the morning peaks. But in some instances, because coal plants are quite inflexible, you may even need to pump a bit at night just to avoid switching off your coal plants. So there are multiple opportunities, but this kind of analysis is very, very interesting if you want to understand how coal plants operate. So uh, estimating the inflow has been quite a big challenge. I've been using the GRDC run database, local measurements from site. Sometimes I have to take precipitation measurements and relate it to the inflows, as well as some of environmental impact assessment reports. So an interesting case is the practicality of modeling hydropower is not always that simple. This is the Zambezi River. On the border of it's on the border of Zambia, Zimbabwe, and Mozambique. Not all of the plants supply power to the same country, and they all operate in a cascade that needs to be coordinated. So what would I like to talk about in terms of improving the representation of hydro and PyPSA? So we have to recognize hydro is a significant contributor to the energy mix. It's a strategic opportunity in terms of flexibility. And we need to find a way to balance the modeling detail without skewing the outcomes that we need to understand how to capitalize on this asset. And it's going to be very valuable if we can start coordinating a generalized approach to representing hydropower in PyPSA. Thank you, everyone, and please feel free to reach out if you have any questions.
Thanks a lot for the talk. It's always good to see when new features are actually used. Do we have questions?
On your last point, would you require changes to the PyPSA framework itself to do that coordinating representation? Or is this something a bit more an abstraction layer which you'd do beforehand, and then you'd abstract several plants away into a single plant, for example, in PyPSA? Is this something you see sitting in the layer above PyPSA, or do you need changes in the PyPSA core?
At the moment, I think the PyPSA core is good enough. If we and it's more, at the PyPSA Earth level, what kind of representation that they would like to have the data flows. I've thought about us looking into a class for hydro, but I'm not sure whether that's worth the juice is worth the squeeze in that case. We'd have to think about the value of that, of representing the hydro components as a separate class. It might just be a bit too complicated from a management perspective.
It sounds primarily like a data issue then.
Yeah, it's more data. Yeah.
There's a question in the chat.
Yeah, there's a question in the chat questioning the accuracy of hydro results and how to validate them.
Well, the accuracy has been quite good. One of the analyses I've done, we're comparing it to the actual operations as well as other commercial tools, and we got very similar outcomes. And at the end of the day, the maths is the maths. So all the optimization tools are kind of doing the same thing. But when you're working on these things practically, it's often about the relationships and understanding what works when, um, and getting a sense of the operational characteristics or how the plants behave more than the actual like pure numerical validation. Kun, yes, I have looked at stochastic optimization. I think where stochastic optimization becomes complicated is in terms of the computational cost. Albra's got a hand up.
Thank you for this opportunity. I asked the question above about the accuracy because now I'm modeling Sudan system. In Sudan, we have 6 hydro dams. So maybe 6% or 20% of our energy came from dams, and it's variant from in size. So I have mixed data from the resources you presented, and I have some ground truth data from the hydropower plant. So I didn't get final result because that I asked about the accuracy of the data and how to validate.
Yeah. Yeah, it really depends on the input data. Yeah.
Maybe
Justin Fields, yes. Yeah.
if you have time, we can keep in
We
touch.
can have a chat. Yeah.
Okay. Thank you. Thank you.